Okay, this is homework from section 4.4. I'm going to go through problems 40 through 48. 48 is not in your homework set, but it's a good problem, so we're going to take a look at it. In this section, we're supposed to find the slope formula, or the derivative, and we are also supposed to state domain. So the first thing I'm going to do is look at the domain of f and see if anything interesting pops up here. But typically on logarithmic problems, we have some domain restrictions, but the key is the argument x squared plus 1 has to be greater than 0, and it is always greater than 0. So we don't run into any points of discontinuity here. The only issue is, might we have a cusp, and hopefully that would be revealed and when we go through the derivative process, that we'd have something peculiar pop up in the derivative. So let's see what happens here. So we want number 40. We want to go ahead and take the derivative of this. So f prime x is ln's derivative. Should be getting pretty good at this by now. I lost my little cheat sheet slip. Must have fallen on the floor or something, but that's good news because it forces us to remember this. Derivative of ln wants to be 1 on the argument. So this wants to be 1 on x squared plus 1. However, we have to take that times the inside derivative, so that's times 2x, and I get 2x on x squared plus 1. So 2x on x squared plus 1 is my slope formula. The only question is, did that present any problems with x? So no, it did not. So I expect that we have all real numbers for our domain, as opposed to problem number 38, where we had some restrictions. We'll probably see some restrictions momentarily. Okay, let's look at number 42. Number 42, f of x is given as log base 10 of square root of x plus 1, which we might want to think of as log base 10 of x plus 1 to the 1/2. In fact, we could pull that 1/2 out in front if we chose to. I'm going to leave it just for the sake of leaving it. Now, first thing I notice here as far as domains go, x has to be greater than or equal to -1, and maybe some other problems are going to pop up as well on problem number 42, but definitely x has to be greater than -1, because this graph, I could take the square root of 0, but log base 10 is the exponent that turns 10 into this number, and 10 cannot be turned into 0 with an exponent. Therefore, and I expect this to grow forever. I don't know exactly where this thing goes, but it's going up to the right as x gets bigger. So let's go ahead and find our derivative. Log base 10. Did I lose that one? I've still got that one. So our log, when it's not e, wants to be just like ln, where we get 1 on the argument, but we have to compensate for this not being e by taking log base e of that, sort of like change of base, and then we have to multiply by the inside function's derivative, which is this or that. So we get 1/2 x plus 1 to the -1/2. Treat the baby, but the derivative of the baby is just 1. So let's clean that up. All that's left for the numerator is a 1. In the denominator, I get a 2. I get another square root of x plus 1 times this. So that's times x plus 1 times ln 10. Let's see how the back of the book simplifies that. That is exactly what they have. I might put the ln 10 in front of the x plus 1 because this is a constant. Does anything new pop up that wasn't included in our domain? No, so our domain is x is greater than -1. Now, notice, here's why we need to list that on problems. Yes, -1 is clearly a problem, but when I come up with this, this would imply, if I just said that the derivative of some function was this, without that, this would imply that I could put -7 in here, 1 on 2 times -6, -12 times ln 10, no problems. But the graph doesn't exist out at -6, so we have to be careful with that. We have to figure out where the graph exists beforehand, before we just say, hey, the slope is this, whatever, put any number in there, we're going to get the slope. Yes, it's implied x cannot be -1, but it is certainly not implied that x cannot be negative 20, for instance. Okay, so that is 42. Let's take a look at 44. They shift directions on us a little bit here, but I want to continue with this rather short video. Here we have y equals tangent of x. And this is cool. We're going to use the technique of logarithmic differentiation. And sometimes this is just an exercise, and other times it's really, really useful. This is not just tangent of x, however. This is x tangent of x. Otherwise, there's no way we'd be using logarithmic differentiation. Sorry about that. So, logarithmic differentiation, we take the log of both sides. You can take log whatever base you want, but we understand that we're using log base e, or ln. The calculus is easier. So when I take ln of x raised to the tangent x, the payoff here is I get ln equals tangent of x times ln x. And now if we take the derivative, because we haven't yet, we get 1 on y dy dx equals, this is a product rule. I want tangent of x times ln of x's derivative, 1 on x, no inside function, plus tangent's derivative, secant squared of x times plain old ln x. And for dy dx, all I need to do is multiply both sides by y. So if I multiply both sides by y, I get y here, but y is equal to this. So instead of multiplying by y, I'm going to multiply this side by y and this side by something equal to y. And I get dy dx equals x tangent to the tangent of x times tangent of x on x plus secant squared x ln x. And that is actually the back of the book answer. Pretty cool. Okay. And problem number 46, one more of those. When we had a problem similar to this in the notes, I didn't do it justice for how much logarithmic differentiation can help, but we battled through it, we got it. I'm going to go with this one. This is going to look really ugly for a bit. We've got y equals, I'm going to leave a blank here just because I'm running out of space on this sheet of paper, x square root of x squared plus 1 all on x plus 1 raised to the 2/3, and we're supposed to find the derivative of this through logarithmic differentiation. How could that be helpful to muddy the water even more with this ln? Let's see. ln y equals, this becomes ln x plus ln of this factor, but that's to the 1/2, so I can pull a 1/2 out, ln of x squared plus 1, minus ln of the denominator factor, but I can pull a 2/3 out of that, times ln x plus 1. And now if I differentiate, I get 1 on y dy dx equals, I'm going to leave a big blank here, and you'll see why in just a minute. You may be able to predict why. The derivative of ln of x is 1 on x. Here I get plus, that 1/2 will survive. It's 1/2, or 1 on 2, x squared plus 1, treat the baby, times 2x, minus 2 on 3, x plus 1, treat the baby, times 1. But now I could multiply this side by y, since y equals, I should have left that, y originally equaled, before these ln's were here, y was just equal to that. I can multiply by x times square root x squared plus 1 on x plus 1 to the, was that 2/3? I believe it was 2/3, yes, to the 2/3. If I multiply by that, I've got dy dx equals, the only thing I could do that remains on that is clean up that second term a little bit in the parentheses. And I get 1 on x plus the 2's cancel, 1 on x squared plus 1 minus 2 on 3. If you like, 3 times quantity x plus 1 or 3x plus 3. So pretty darn slick when we get a whole bunch of, this is quotient rule. We'd have to go quotient rule with this and product rule with that, and there's no way we could get to this in that kind of timely manner. So loves me some logarithmic differentiation when it can help us out. All right.